This is the last part of the unit on molecular structure and bonding, where we're going to look specifically at molecular orbital theory for heteronuclear diatomics. Okay, we handle these very differently to homonuclear diatomics. And the way that we do that is we look at the orbital potential energies, and then we calculate if an interaction between orbitals is going to occur. The rules for doing this will follow on the next few slides as I work through them, but you're going to focus particularly on table 5.2, where we look at the energies in electron volts for each of the orbitals. Now, this information will be given to you. It's not expected that you know it. So in asking to do an example, you'll be given the values for the different orbitals, and then you can make the decisions from there. Okay, so basically it's a two-step procedure. You're going to calculate the energy difference between orbitals, and then you're also going to determine which orbitals have the same symmetry. With heteronuclear diatomics, you need to remember that orbitals are going to have unequal contributions from each atomic orbital. Okay, remember with homonuclear, the energy levels of the atomic orbitals were placed at equal energy, and then we decided where the molecular orbitals went from there. In this case, we have to go with the orbital energies and make decisions from there. Okay, so essentially the wave function is going to be a linear combination of the atomic orbitals, but the energy contributions are going to be very different. All right, so in this case, we're not going to get an equal contribution. And we find that if, for example, the energy contribution from atom A is much greater than for atom B, then we're going to find that the electron in that orbital is going to be nearer to atom A than atom B. And obviously the reverse is also true. If the electron density of or the energy of the orbital is much larger, then the orbital is going to be mainly focused towards atom B and is going to be nearer to B than atom A. And another thing to remember is that the more electronegative element is going to make a larger contribution to bonding orbitals, while the less electronegative elements will make a larger contribution to anti-bonding orbitals. Okay, so this is the general molecular orbital diagram for two atomic orbitals with different energies. So if we take a look at the atom on the left over here, so this will be for atom A, and this will be for atom B. We have the atomic orbitals for A and B. You can see that atom A has lower energy than atom B, and in this case, as I've said to you, you'll see that the major contribution for the bonding orbital, this will be the bonding orbital over here, and this will be the anti-bonding orbital over here, and you will see that the major contribution for the bonding orbital goes to atom A, while the major contribution for the anti-bonding orbital is closer to atom B. This is all decided from the orbital energies, from that table that I will give you. Okay, so the easiest thing for us to do would be to work an example. Okay, I'm going to go through it here, and then I'm going to do it again on a separate slide so that I can actually show you how to construct the orbitals, because the slides already give you pictures with pre-constructed orbitals, but I want you to see where exactly they come from. So in this case, for carbon and for oxygen, we're going to obtain the energy values for the orbitals from table 5.2. And we have orbital energies for the 2s orbital, which is 19.43, and we have the energy contribution for the 2p orbitals for carbon, which is minus 10.66. The units for this is in electron volts. Okay, so if now we look at the orbital energies for oxygen, for the 2s orbital is minus 32.38 electron volts, and for the 2p orbital is minus 15.85 electron volts over here. Okay, now the major thing to remember is that orbitals with an energy difference of more than roughly 13 electron volts, they don't interact, and that sort of non-interaction is going to result in a non-bonding orbital. But we'll get to that. We'll do an example where such a case exists. All right, so now how do we determine how the interactions take place? Well, we need to have a look and see that the 2s orbital for carbon, is it going to interact with the 2s orbital from the oxygen? Well, we need to calculate the difference. Okay, so we're going to take minus 32.38. Okay, so minus 32.38 minus the minus 19.43. Okay, and you're going to find that that answer is going to give you 12.95. Well, actually it's minus, but we're working with the actual values here. So it's absolute value, sorry. So it's 12.95 electron volts, which is just on the cusp of this limit where I've told you that the 13 electron volts is an interaction. So we're going to get an interaction with the carbon and the oxygen 2s. And obviously we're now going to get an interaction with carbon 2p orbitals and oxygen 2p orbitals. Let's have a look at the difference here. So in this case, it's minus 15.85 minus 10.66, and that should give you 5.19, okay, minus 5.19, which means that there'll definitely be an interaction, okay. And then lastly, we need to also consider, is there possible orbital mixing? Remember that these are atoms in the second period, and when we looked at orbital mixing, we get S and P mixing. Is it possible? So we need to have a look at, is the 2s from the carbon going to mix with the 2p for the oxygen? And if we do that, we do get a difference. So the 2s is, let's see, so that's the 2p and the 2s. So we've got minus 19.43 minus 15.85, and you should see that the difference will probably give you this answer over here. So there is orbital mixing. Okay, so that means you need to remember what happens when we get orbital mixing. We need to swap the pi and the sigma orbitals around, the molecular orbitals. Okay, so let's see how we do this. Okay, so this is what the molecular orbital diagram for the carbon monoxide is going to look like. Okay, I'm going to explain each step as to how we ended up with this entire diagram here. In other words, why does it look like this? Why here is carbon, okay, so we've got the 2s of the carbon over here, and we've got the 2p of the carbon over here, and we've got the 2s of oxygen here and the 2p of oxygen here. Why do the orbitals look, the molecular orbitals in the center of the diagram, okay, remember these in the center of the diagram over here, why do the orbitals look like this, and where do they come from? Okay, so let's see exactly where they come from. All right, so the first thing we're going to look at is we're going to look at this orbital down here, which is the sigma bonding orbital for the interaction between the 2s of the oxygen and the 2s of the carbon. Okay, so that is an S-S bonding orbital, and the energy contribution is going to be mostly from the oxygen 2s. So you can see that it's closer down here, it's not so far away. Okay, and then the next one is the anti-bonding orbital, which is this one here. Okay, so that's the anti-bonding orbital for the interaction between carbon 2s and oxygen 2s. And you will actually see that this anti-bonding orbital is lower in energy than the 2s of the carbon. Okay, so, and the energy contribution is a little bit different, but this one is mostly this sigma star for the 2s is mostly related to the 2s for the carbon, and this bonding orbital down here, so I'm going to put 2s and 2s. You will see that this one relates to carbon and this one relates to the oxygen. Okay, so that explains the formation of the molecular orbitals when we overlap the 2s orbital from carbon and the 2s orbital from oxygen. Okay, now let's go to the 2p orbitals. All right, remember we have orbital mixing, so that means that the pi orbitals down here, where it says pi 2p, these contributions will come from the pi x and the pi y orbitals. Okay, it's a bonding interaction between the 2p of the 2p x and y of oxygen and the 2p x and y of carbon, and the energy contribution comes mostly from the oxygen atom again, because remember the oxygen is the more electronegative of the two atoms. Okay, then the anti-bonding interaction, so this will be the pi bonding, okay, from the px and the py. The anti-bonding interaction is this one up here, so that's the anti-bonding interaction. Okay, and then so you have the 2px and 2py of the respective atoms formed in this manner, and you can see that the way that, because the pi bonding orbital is lower in energy than the sigma, it indicates that there's orbital mixing, which I've already explained. Okay, now let's have a look at this orbital here. This is the sigma bonding orbital from the pz interaction. So we've got the oxygen 2pz and the carbon 2pz. That forms the sigma bonding interaction, which is indicated as I've drawn it. And then lastly, we've got the anti-bonding coming from the pz orbitals over here. So that's how we construct the diagram. Okay, filling of the electrons I will explain in a separate slide, so that you can see exactly which electrons come from where and how to fill this orbital, because this diagram is showing you that the orbitals are already filled. What I wanted to explain here was where the orbitals are actually positioned. Okay, so there's one more thing that we need to explain with the carbon monoxide example, is something which we talk about in terms of the notation on the molecular orbitals. We specifically want to define something new. It's called a frontier molecular orbital, and there are two of them. The first one is called a HOMO, and that is designated HOMO for the highest occupied molecular orbital. So that's where the word or the acronym HOMO comes from. And then the next one is the LUMO, which is then the lowest unoccupied molecular orbital. All right, now you can see that if we looked at just the molecular orbitals, remember that the molecular orbitals sit in between the two atoms when we draw the diagram, and we see that the highest occupied molecular orbital is the sigma bonding orbital that's as a result of the pz interaction. Okay, so this here is the HOMO. That's the highest occupied molecular orbital. And then, of course, the LUMO is now the pi star orbitals. Okay, so that's the pi star orbitals. So that is the lowest unoccupied molecular orbital. All right, so that's how we designate these frontier molecular orbitals. They're important because as you move on to higher levels of chemistry, you're going to see how the impact of the HOMO and the LUMO is. All right, regarding the bond order, I'm going to do that in a separate video. when I show you exactly how to fill the diagrams accordingly. Okay, let's do a second example with hydrogen fluoride. HF, is quite a big electronegative difference between the hydrogen atom and the fluorine atom. So therefore, the molecular orbital diagram is going to look very different to what you would expect it to be. Okay, so what we need to know is the orbital energies. Remember, I will give you the table that you can look up the values, or else I will simply give you the values and then you can work from there. Okay, so for example, now let's have a look at hydrogen. Hydrogen has only one orbital that we're aware of, and that's the 1s orbital. And therefore, the orbital energy of the 1s orbital is listed as minus 13.6 electron volts. Okay, there's no units here, but remember it is electron volts. You can go back to the table and check. And then you will see with fluorine, for the atomic orbitals, we've got a 2s and a 2p. So the interaction, or the orbital energy for the 2s is minus 40.17 electron volts, and the 2p is minus 18.7 electron volts. All right, so the first thing we need to do is look and see, are we going to get an interaction? So we must first take the linear combination of orbitals and say, okay, is the H1s going to interact with the F2s? Well, no. Look at the difference between the two orbitals. If we say minus 40.17 minus 13.6, you see we're going to get 26.57. That's too much of an energy gap. There's not going to be an interaction. Okay, but if we looked at the 1s for the hydrogen and we try to see if there's an interaction with the 2p of the fluorine, then we get a difference. Have a look here, 18.7 and 13.6. We get 5.1 electron volts. That's good enough for there to be a bonding interaction taking place. All right. Sorry, excuse me. So now, how do we draw this, and why do we end up with this molecular orbital diagram here, which looks very weird? Let's see how we're going to put this together. Okay, so the SS bonding orbital that is formed is only formed from the 2s of the fluorine. We don't even get it as a bonding orbital. It's actually a non-bonding orbital. So if we looked here, remember that the energy gap between the 1s of hydrogen over here to the 2s of fluorine is too big for an interaction to occur. So what happens is that it forms a molecular orbital, but it's classified as a non-bonding orbital. So these two electrons will sit in this non-bonding orbital. There's no interaction whatsoever. Okay, but what does happen is that we do have an interaction between the 1s orbital and the 2pz orbital. Okay, so if this one is the pz, okay, let's do that, and then this one here is px, this one here is py. So the pz orbital is going to interact with the 1s orbital of hydrogen to give us the sigma bonding interaction down here. So this electron here and this electron here will sit in this orbital here. I will also do this in a separate video so that you can see how the electrons are filled. Okay, now the remaining electrons, there are 4 of them from the 2p orbitals of fluorine. They can't interact with any more electrons from hydrogen, because hydrogen only has 1 electron. So therefore the pi orbital here is just going to be a non-bonding orbital, and of course then you're going to have the anti-bonding orbital up here as a result of the corresponding 2 orbitals from the pz and 1s interaction. Okay, so that's how we construct the molecular orbital diagram for HF. Okay, so again, this is just further explanation that the sp antibonding orbital comes from the F2pz and the H1s, and the energy contribution is mostly from the 1s orbital, and then the pp non-bonding orbitals from the fluorine 2px and 2py energy contribution. There are no similar symmetries. Remember that you have an s orbital, which is spherical, and then you have 2p orbitals. There are no overlapping symmetries, and that is why these guys become non-bonding orbitals. Again, with the calculation of the bond order, I will do that in a separate video so that you can see how we determine the bond order there.